Okay, today we will continue with a capacitor in AC circuit. First, let's talk about capacitor. What is capacitor? What is it used for? Capacitor is a device which is used to store electric charges. A simplest capacitor has two parallel conducting plates like this. Their symbol is like this. Also, these lines are representing the conducting plates. When a capacitor is attached to a battery with the negative and positive terminals, like this, if you connect them, so the one plate which is attached to the negative terminal becomes negatively charged, and opposite plate becomes, which is because it is attached to the positive terminal of the battery, positively charged. So this is the capacitor. This is the capacitor, and it is used to store electric charges. So because these electric charges carries the energy, so it is used to store electrical energy. And capacitors are devices which are used to store electric charge, which is Q, and also which is used to store electrical energy. And every capacitor has a capacitance represented by C. And when you attach this capacitor to a potential difference V, this capacitor stores a charge which is equal to Q C times V. And if you multiply capacitance of the capacitor with the potential difference across the terminal of the capacitor, you are going to calculate the charge accumulated on the plate of the capacitors. So when a capacitor is empty, because initially there is no charge accumulated, because uncharged initially the capacitor, potential difference will be zero. But when you attach a capacitor to battery like this, let me draw here again. So this is the this is the battery. So a negative and positive terminal of the battery. If you attach a capacitor to a battery, of course we need a switch here. Assume that switch is initially open. When it is open, of course, there will be no charge stored in the capacitor. There will be no polarization of the plates, so there will be no potential difference. Potential difference between the plates of the capacitor will be zero. But as soon as you closed the switch, electric charge starts moving from this battery to the plates. And because initially the capacitor is completely empty, maximum number of electric charge will start moving from the battery to the capacitor. So for that, as in for an empty capacitor, when it's empty, initially, and as soon as you switch it on, electric current becomes maximum. So empty capacitor draws maximum electric current. But because initially there is no charge, potential difference becomes zero. So then potential difference we see between the ends of the capacitor will be zero because there is no polarization. Potential difference we see across the capacitor is zero. But as time passes, this capacitor starts to be charged. Initially, one charge, one negative, one positive. Later, two negative, two positive. Then three negative, three positive. As time passes, so then polarization, capacitor becomes polarized, and then this causes an increase in potential difference. So, and then finally, capacitor becomes completely charged, and there is no space for additional charges to move. So then, when it's completely charged, potential difference between the plates of the capacitor becomes maximum. But because there is no space for additional electrons or additional charges, electric current flow from battery to the capacitor will be zero. So that's why fully charged capacitor, so electric current becomes zero because there is no empty space for additional charges, but potential difference becomes maximum because capacitor is completely polarized. For that reason, electric current potential difference through the capacitor changes inversely. And when capacitor is empty, So maximum current is flows through the capacitor, but potential difference becomes zero. But when the capacitor is completely charged, electric current becomes zero, but potential difference becomes maximum. So that's why when you connect this capacitor to an AC circuit like this is the capacitor and this is the AC generator. And then if you want to measure the potential difference across the terminal of the capacitor and the electric current through the capacitor, so you are going to observe that voltmeter reading and ammeter reading are opposite. When ammeter reaches the maximum, and when this capacitor draws the maximum current, potential difference, because capacitor is uncharged, potential difference becomes zero. So that's why reading of the voltmeter and ammeter also changes inversely. As voltmeter reads zero, which means it is uncharged, ammeter reads maximum because it is the maximum number of electrons starts moving to the capacitor. When voltmeter is the maximum, which means capacitor is completely charged, so ammeter is zero because electric current will be zero. Or if the voltmeter reading is increasing, which means capacitor is becoming charged, so electric current in the capacitor flowing into capacitor decreases, which is the capacitor is charged. And when the voltmeter reading is decreases, which means it becomes uncharged, so ammeter reading increases. So that's why voltmeter reading and ammeter reading in a capacitor also inverse is changing. And this fact is defined, remember, the same as the inductor being out of phase. In the AC circuit, when you attach a capacitor to a generator, reading of the voltmeter and ammeter inverse is changing. And this is zero, this is maximum. This is zero, that is maximum. If the reading of ammeter increases, the reading of the voltmeter decreases, out of phase. But here, there is the difference between the inductor and the capacitor. Here is the electric current is leading, because when it is empty, it draws the maximum current. We will start the maximum current. But because capacitor is initially empty, potential difference is zero. And potential difference is late. Potential difference is late. Electric current, as soon as you switch on the circuit, electric current becomes maximum. For that reason, we say that in a capacitor, the potential difference across the capacitor, we see lags behind the electric current, and electric current is leading, but potential difference is lags behind. So potential difference lags behind the current by a phase angle of pi over 2. This is opposite of inductor. Remember, in inductor, potential difference was leading the electric current, but now in capacitor, potential difference is lags behind the electric current by phase angle of pi over 2. Okay, this drawing is better explaining that. As I said, as soon as you switch on the circuit, potential electric current is maximum because the capacitor is empty, but potential difference is zero because capacitor is empty. If there is no polarization, there is no potential difference. As reading of the ammeter decreases, reading of the voltmeter increases. When ammeter reaches zero, voltmeter reaches maximum, so out of phase. Again, phase angle difference between the electric current potential difference is pi over 2. So potential difference lags behind the electric current by a phase angle of pi over 2. Lagging by pi over 2 also represented by two vectors perpendicular to one another. So if we represent the electric current in horizontal, in positive x direction, which is I capacitor IC, Im sine omega t, so potential difference must be lags behind the electric current by a phase angle of pi over 2. That's why equation of the potential difference will be Vm sine omega t minus pi over 2. So this is the electric current equation. IC is equal to Im sine omega t. This is the potential difference equation. Vc is equal to Vm sine omega t minus pi over 2. So according to Ohm's law, again, V over IE, Vm over Im defines a property of the capacitor. Again, capacitance, it is the opposition to the electric current, because electric current sometimes becomes maximum, sometimes becomes zero. So then something opposes the electric current flow. So this ratio, according to Ohm's law, VE over IE or Vm over Im defines a property of the capacitor which is known as capacitive impedance and represented by XC. And XC is equal to Vm over Im and VE over IE. It's unit again volt per meter, which is equal to ampere, the same as the resistor. Resistor, XL and XC. These three oppositions are have the unit, the same unit, which is ohm, omega. But their natures are different. In resistor, remember, the resistance, the opposition of the conductor to electric current, because electrons were colliding with the atoms, but XL is the opposition of the coil to the electric current because of the self-induction. But XC is completely different. When capacitor is charged, so electric current becomes zero. And charged capacitor opposes the electric current flow. When it's empty, it can be easily moved, but when it's full, its electric current gets difficult to flow through the capacitor. It's completely different in nature. So capacitive impedance, XC, also defined as the opposition of the capacitor to the flow of electric current. XC also depends on two quantities. One of them is the capacitance of the capacitor. So if capacitance is big, which means so much electric current can flow and difficulty becomes less. That's why XC is inversely proportional with capacitance. Greater capacitance means smaller capacitive impedance. And next one is omega, angular frequency. So 1 over omega C, or 1 over 2 pi fc, is the equation for calculating the capacitive impedance of a capacitor. And here also see that as frequency changes, inductive capacitive impedance also changes, but inversely. If frequency increases, so XC, and in capacitive impedance, decreases. It is opposite of the inductor. In inductor, it was like this. So R does not affect by the F. F cannot affect R. XL, directly proportional with F. So R has zero effect. R is not proportional to, there is no relation between frequency and R, but XL is directly proportional to frequency, but XC is inversely proportional with the frequency. As frequency of the generator or AC circuit increases, XC decreases. So this is the equation for calculating the capacitive impedance of a capacitor. Now let's solve some problems about them. The first question, this problem. Calculate the capacitive impedance of a capacitor whose capacitance is 2 microfarad. So C is equal to 2 microfarad, but this microfarad must be converted to farad. So every micro converted to by multiplying 10 to the power of negative 6. So then C is equal to 2 times 10 to the power negative 6 farad. Calculate the capacitive impedance, and C is the question, of a capacitor whose capacitance is 2 microfarad connected across a source of frequency 100 Hertz. So then frequency of the AC generator or the circuit is 100 Hertz. Calculate XC. Equation for calculating the capacitive impedance is 1 over 2 pi FC. Okay, let's write the given, insert into the equation. 2 pi 6.28 multiplied by frequency is 100 multiplied by capacitance 2 times 10 to the power negative 6. Don't forget the bracket, so otherwise your calculation will be mistake. Now let's do the calculation. So 1 divided by 1 divided by, don't forget the bracket, 6.28 multiplied by 100 multiplied by 2 times 10 to the power of negative 6, close the bracket. So answer is almost 796 ohm. This is the capacitance of the inductive impedance of this, the capacitive impedance of this capacitor. Next question is, an AC source of instantaneous potential difference. This is the generator. Generator's equation is this. Generator equation. Sometimes it's getting confused with some other things. This is generator equation, not belongs to the capacitor. A generator, a source of instantaneous potential difference 10 sine 100 pi t is connected across a capacitor of capacitance 1 microfarad. C is equal to 1 microfarad. Calculate the maximum value of the current. Calculate IM. IM is the question. Maximum value of the current and phase difference between the current and the potential difference. We know about this. Phase difference is pi over 2. So potential difference lags behind the electric current by a phase angle pi over 2. So we will calculate maximum value of the current equation for calculating the maximum value of the current, we need Vm over Xc. This is the Ohm's law. So Vm can be got from the equation because this generator has an equation Vm sine omega t. This is generator's equation. So instead of Vm, it is written 10 sine omega is 100 pi t. That's why Vm is 10, omega is 100 pi. So Vm will be written here, so which is 10, but we need to calculate Xc. Xc should be calculated. Xc is equal to 1 over omega c. So then 1 over omega is 100 pi. 100 pi is 314, 3.14 times 100. 314. C is 1 microfarad. It must be converted to farad by 10 to the power of, multiplying 10 to the power of 6. So that's why 10 to the power of negative 6. Don't forget the bracket. Let's calculate the Xc. 1 divided by 314 multiplied by 10 to the power of negative 6. So answer is almost 3185 ohm. This is the capacitive impedance of this capacitor. And now we insert this into the equation, 3185. So then 10 divided by answer, 10 divided by answer. So it's becoming Im is equal to maximum current 3.14 times 10 to the power of negative 3 ampere. This is the maximum current, maximum current of this circuit, or the maximum current of this capacitor. Next question is a source of frequency 100 over pi hertz, an effective potential difference. So frequency is given as 100 divided by pi hertz. An effective potential difference 200 volt. VE is given, effective value of the potential difference, which is equal to 200 volt. Is connected of a capacitance of 200 microfarad. C is equal to 200 microfarad. So which is equal to 200 multiplied by 10 to the power of negative 6 farad. Calculate the capacitive impedance, Xc is the question. The effective value of the circuit, effective current of the circuit, which is IE, is the question. Maximum charge accumulated across the capacitor, Qm, is the question. Of course, to calculate IE, we need Ohm's law, VE divided by Xc. V is given, but Xc must be calculated. And it's also a question. Let's calculate for first Xc, which is equal to 1 over 2 pi Fc. So 1 over 2 pi, F is 100 over pi, multiplied by C is 200 times 10 to the power of negative 6. Don't forget the bracket. So pi and pi will simplify, and then let's multiply them and do this calculation. So 1 divided, don't forget the bracket, 2 times 100 times 200 times 10 to the power of negative 6, close the bracket. So then this is the answer, which is 25. Xc, capacitive impedance of this capacitor, is 25 ohm. Now we are ready for calculating the effective current. IE is equal to VE. V is given in the question 200 volt divided by Xc 25. We just calculated. 200 divided by 25. Let's do it. 200 divided by answer, which is 8. 8 ampere is the effective current of the circuit. So we got two of them. We got Xc and we got IE. And maximum charge is the next step. Of course, to calculate the maximum charge accumulated, we need the equation for capacitor C times V, but because it's as maximum charge, we should use maximum potential difference. But maximum potential difference is not given. First, let's calculate it. V maximum is equal to V effective potential difference multiplied by root 2. So which means 200 root 2 volt is the maximum potential difference. Now we can calculate the maximum charge accumulated across the capacitor. So C is 200 times 10 to the power of negative 6 farad multiplied by 200 root 2. Let's do this calculation. So 200 multiplied by 10 to the power of negative 6 multiplied by 200 multiplied by root of 2. Answer is 0.056 coulomb. So this is the maximum charge accumulated on this capacitor. So this is all about the circuits. We connected first the resistor in an AC circuit, then inductor, coil into an DC circuit, AC circuit, and then we connected a capacitor to an AC circuit, and then we calculated the charge, we calculated the potential difference, effective current, and then this is all about this section. Next lesson, we will connect all these three elements in series: resistor, capacitor, and inductor in an AC circuit.